morning, all of you. Welcome to CJ in the Bank Zone. Now we are continuing Thermodynamics, Lecture 3. So far we have done Lecture 1 and 2. Now we are going to do Lecture 3. So this is Thermodynamics is over in the previous session. Now we are going to start Thermochemistry. So Thermodynamics and Thermochemistry. Thermodynamics deals with physical processes as well as chemical processes. But Thermochemistry deals with only chemical processes. So I hope it is clear. Now we are going to start Thermochemistry. Very important point. So, so thermodynamics and thermochemistry both are very important. Let us see now. So, now thermodynamics and thermochemistry. So we have done thermodynamics already. So thermochemistry now we are going to do. So let us see what is thermochemistry. Thermochemistry is a branch of chemistry which deals with the energy changes accompanying chemical reactions. So in this we are going to work out based on energy changes. Very important. Energy changes. What are the energy changes? That is heat of formation or heat of decomposition. What are the heat associated with the reaction we are going to discuss with you. That is called thermochemistry. So it is based on first law of thermodynamics. First law of thermodynamics already you know, that is delta U is equal to Q plus W. So thermodynamics and thermochemistry. So now we are going to discuss about thermochemistry. Let us see what is thermochemistry gives us. Now, what is thermochemistry? Thermochemical equation. Thermochemical equation. So it is a balanced chemical equation which represents the physical states of reactants. Very important point here is balanced chemical equation. So if the equation is given, first we have to check whether it is balanced or not. It is a balanced chemical equation which represents the physical states of reactants and products along with the enthalpy change of the reaction. So this is called thermochemical equation. So we'll continue with enthalpy change of the reaction. So in this case, we'll find. So for example, when 1 mole of carbon is burned with oxygen gas, it forms carbon dioxide gas. And in this case, it was found it is an exothermic reaction. Delta H is minus 393.5 kilojoules per mole. So for the formation of 1 mole of carbon dioxide, this much of energy is released. How much energy? That is enthalpy changes minus 393.5 kilojoules per mole. So as it is given minus, it is released. Minus means released. Plus means absorbed. So similarly for the formation of water, when 1 mole of hydrogen comes with half mole of oxygen gas, it forms 1 mole of water. And delta H in this case is minus 285.8 kilojoules per mole. So this is called thermochemical equation. Thermochemical equation means we'll accompany with the enthalpy change. So it is a balanced chemical equation which represents the physical states of reactants and products. So here the physical state of reactant is carbon solid, oxygen gas, carbon dioxide gas. Similarly, hydrogen gas, oxygen gas, and water is also liquid. So it represents the physical states of reactants and products along with the enthalpy change. Here delta H is must. So along with the enthalpy change. On the whole, this is called a thermochemical equation. Thermochemical equation. I hope it is clear. It's very easy to understand and more important and more confusing also. Definitely from this topic, you'll get a question for entrance exams. Now, what are exothermic reactions? Already we know the reactions in which heat is released or evolved or liberated. Evolved, released, or liberated. All the three are same. So heat is evolved or released or liberated. So all the three are same. So the equation, a chemical equation in which it accompanies with the release of heat or liberation of heat or evolution of heat, it is called as exothermic reaction. In exothermic reactions, energy of reactants is always greater than energy of products. That's why you'll be getting negative. So C plus O2 gives way to CO2. It is plus 34.3 kilocalories. It means plus C on the right hand side means it is exothermic reaction. Actually, this reaction can be written as like this also. We can see here C plus O2 gives rise to CO2. Delta H is minus 34.3 kilocalories. So actually representation of this reaction is like this. It states that as heat delta H is negative, we'll say heat is released or evolved or liberated, and hence it is called as exothermic reaction. So in this way, you can represent the same. Since delta H is negative, negative on the left hand side you cannot write, so we'll take it to right hand side. So it becomes positive. So 34.3 kilocalories. Similarly, 2H2 plus O2 gives us 2H2O. This is also an exothermic reaction. It releases 114 kilocalories. Heat is measured in joules, calories, etc. So already we know, and we know the conversions also. 1 calorie is equal to 4.2 joules. This already we know. So for this also we can write the equation as 2H2, 2 moles of hydrogen gas combined with 1 mole of oxygen gas to form 2 moles of water gas. So water vapor, and in this case delta H is equal to negative, that is minus 114 kilocalories. So I hope it is clear. So like this we have to write. This is called exothermic reactions. What are exothermic reactions? Exothermic reactions are the chemical reactions in which heat is evolved. Simple. So in these exothermic reactions, always energy of reactants is greater than energy of products. That's why we are getting negative value. I hope it is clear. Next. What are endothermic reactions? Endothermic reactions are reactions in which heat is absorbed. Delta H is positive. So energy of, in this case, energy of reactants is always less than energy of products. Energy of reactants is always less than energy of products. For example, carbon on reaction to sulfur, it forms carbon disulfide. Delta H is plus 92 kilojoules per mole. How we write this equation? This equation we can write like this straight away. C plus 2s, that is carbon solid, plus sulfur solid combines together, plus, and here we have to take plus here because it is endothermic reaction. So plus 92 kilojoules per mole, 92 kilojoules per mole energy gives rise to carbon disulfide liquid, gives rise to carbon disulfide liquid. So this is the equation. So since delta H is positive, so we have to write left hand side only positive. If you are taking delta H negative, left hand side negative. That's why other side we will write positive. I hope it is clear. This is the clear differences between endothermic and exothermic. And endothermic reactions, energy of reactants is always less than energy of product. Similarly, H2O plus O, liquid changes to H2O gas. For this, we have to give some energy. So that energy is equal to 47.3 kilojoules per mole. For this reaction, we can write H2O liquid plus how much energy we are giving to convert liquid into gas. 47.3 kilojoules per mole gives rise to 47.3 kilojoules per mole gives rise to H2O gas, that is vapor. I hope it is clear. So this is called endothermic reactions. Endothermic reactions, delta H, heat is observed. Heat is observed. Whereas exothermic reaction, heat is released. I hope it is clear. Next. What is heat of reaction? The heat of reaction is defined as the amount of heat evolved or absorbed. Either it can be endothermic or it can be exothermic. Evolved means exothermic, absorbed means endothermic. When the number of moles of the substances indicated by the balanced chemical equation have completely reacted. So the whatever the heat of reaction is nothing but it is defined as the amount of heat evolved or absorbed when the number of moles of the substances indicated by the balanced chemical equation have completely reacted. Heat of reaction at 298 kelvins and 1 bar pressure is known as standard heat of formation. What is standard heat of formation? It is nothing but standard heat of formation is delta H, sorry, HF. Will generally heat of formation is taken as HF. Change in heat of formation is delta HF. Similarly, when heat of reaction is taken at 298 kelvins room temperature and 1 bar or 1 atmospheric pressure is known as standard heat of formation. For this we let heat of formation is equal to standard heat of formation H degree F. It is nothing but standard heat of formation. Delta H degree F is called enthalpy change of standard heat of formation. Enthalpy change of standard heat of formation. So these are the terminologies. Terminology is very, very important. So heat of reaction at 298 kelvins and 1 bar pressure is called as standard heat of reaction, and it is denoted by the letter HF degree. And enthalpy change in standard heat of formation delta HF degree. What is heat of formation? HF. What is heat of formation of enthalpy change in heat of formation? Delta HF. Delta HF is called enthalpy change in the heat of formation. Or you can say change in enthalpy, enthalpy change, or enthalpy. This is taken as enthalpy simply. In other words, enthalpy of formation, enthalpy of formation, and this is enthalpy change of formation. And now what is this? This is called standard enthalpy of formation, or standard heat of formation, or enthalpy of formation. Standard heat of formation or enthalpy of formation, both are same. Standard heat of formation, and this is called standard enthalpy change formation. Standard enthalpy change or heat change formation. Enthalpy change formation. I hope it is clear. So please note it down. This is called heat of reaction. Next, heat of reaction under different conditions. The amount of heat absorbed or evolved during a chemical reaction may depend on whether the reaction is carried out at constant pressure and constant volume. So if the reaction is carried out constant pressure and constant volume, these two are very important. The previous session only we have discussed what is constant pressure and what is constant volume. So the amount of heat absorbed or evolved during a reaction may depend. It depends upon two conditions, that is at constant pressure, whether the reaction is carried out at constant pressure or the reaction is carried out at constant volume. So that is called heat of reaction under different conditions. I hope it is clear. Next. So the heat, what is heat of reaction at constant pressure? Delta H. It is also called as delta H. Heat of reaction at constant pressure is the difference between the enthalpies of products and reactants. Enthalpy, sigma of enthalpy of products minus sigma of enthalpy of reactants. Together it is called as delta H. That is called heat of reaction at constant pressure. Heat of reaction at constant pressure. For exothermic reactions, delta H is negative because sigma heat of products minus sigma heat of reactants is less. So that's why it is negative. And for endothermic reactions, delta H is positive because sigma H of products is greater than sigma H of reactants. So now we can understand better why exothermic reactions delta H is negative and why in endothermic reactions delta H is positive. Since in exothermic reactions we already know that the energy of products is less than energy of reactants, so that's why it is negative. And in endothermic reactions the energy of products is greater than energy of reactants, that's why it is positive. I hope it is clear. So the heat of reaction at constant pressure is called delta H. Delta H is called what? Heat of reaction at constant pressure. Heat of reaction at constant pressure is called delta H. This is called as delta H. I hope it is clear. And this is it is nothing but what? The difference between enthalpies of products minus enthalpies of reactants. And for exothermic reactions, delta H is equal to QP, which is also equal to sigma. Sigma means all the products minus sigma H means all the reactants. So minus sigma enthalpy of all the products minus enthalpy of all the reactants. If it is one or two, whatever it can be. Next, similarly for exothermic reactions, delta H is negative because it is equal to, since enthalpy of products is less than enthalpy of reactants. Enthalpy of products is less than enthalpy of reactants. For endothermic reactions, delta H is positive because enthalpy of products is greater than enthalpy of reactants. So please note it down in your classwork so that you will not get any confusion while solving numericals based on this. I hope it is clear. Next. What is heat of reaction at constant volume? It is denoted by the letter delta U or delta E. Also, it is called as delta E. Delta U or delta E is same, that is change in internal energy we'll call, but it is also called as heat of reaction at constant volume. Heat of reaction at a constant volume. Let us see now. Heat of reaction at constant volume is the difference between the internal energies of the products and reactants. That's why we call it as volume, delta U. Why it is called? It is the difference between the internal energies of products and reactants. So delta U is equal to sigma U of products minus sigma U of reactants. And for exothermic reactions, same, that is delta U is negative because internal energy of products is less than internal energy of reactants. Similarly, for endothermic reactions, delta U is positive because internal energy of products is greater than internal energy of reactants. I hope it is clear. So this is called heat of reaction at constant volume. So heat of reaction at constant volume is determined by the letter delta U, which is also called as delta E. Delta U or delta E both are same, because in some books they have represented it as delta E. It is nothing but simply it is better to delta E, because delta U is already change in internal energy. So that's why. So here the heat of reaction at constant volume is the difference between the internal energies of the products and the reactants. I hope it is clear. Next. So based on this, you will definitely get questions. Now relation between heat of reaction at constant pressure and heat of reaction at constant volume. Since already we know delta H, that is heat of reaction at constant pressure, is equal to delta U, that is heat of reaction at constant volume, plus delta NGRT, where delta Ng is equal to sum of number of moles of gaseous products minus sum of number of moles of gaseous reactants. In the previous lecture also I have done this type of numericals. So sum of number of moles of gaseous products minus sum of number of moles of gaseous reactants. Only gaseous is important, because here we'll consider only gas. We'll not consider liquid or solid. So gaseous products and gaseous reactants are important. So for example, let us see how to calculate delta N. 4 moles of carbon monoxide gas, hydrogen 8 moles, 3 moles of methane forms, and 1 mole of carbon dioxide, 2 moles of water. So water we will not consider. So here 1 plus 3, 4. That is 3 plus 1, 4. 3 plus 1, 4. Minus products minus reactants, 4 plus 8, because both are gases. So it is equal to 3 plus 1, 4. 4 minus 12, it is minus 8. So for any reactions involving only solids and liquids, delta Ng is equal to 0. And therefore delta H is equal to delta U in that case. So for reactions involving only solids and liquids, only solids, you should not have at least one gas also. So for the reactions involving only solids and liquids, delta Ng is equal to 0. I hope it is clear. Therefore, since delta Ng is equal to 0, so delta nRT becomes 0. So delta H is equal to delta U. I hope it's clear. So this equation is very, very important. This we are dividing in the previous session only, that is 9.4. Based on this, definitely you'll get numericals. What is delta H? Heat of reaction at constant pressure. What is delta U? Heat of reaction at constant volume. So heat of reaction at constant pressure and heat of reaction at constant volume. I hope it is clear. Let us see now. Question based on this. Yes. Simple. This question already we have done in previous lecture. So again, we are doing with similar values. Calculate the difference of heat of reaction at constant pressure, that is delta H. Heat of reaction at constant pressure is called what? Delta H. And that of at constant volume, that is heat of reaction at constant volume, that is delta U. For the combustion of 2 moles of liquid benzene at 25 degrees C. So first, any organic compound on combustion gives what? Carbon dioxide and water. So benzene liquid. Benzene is an organic compound, so C6H6 liquid on reaction with oxygen gas, that is combustion is oxygen, it forms carbon dioxide and water. And they are given 2 moles. 2 moles means how many moles of liquid benzene? 2 moles. So here, this is called combustion equation. So delta H minus delta U is equal to delta N RT. Delta N is called what? 2 moles of liquid benzene. So 2 moles of liquid benzene. So for this, we have to calculate delta N. Let us see the calculation of delta N. So for 1 mole, we know, and 2 moles also. For 6 carbons, so see, we keep 6 carbons here. First, we'll balance carbons, then hydrogens. So 6 hydrogens means 3 hydrogens. Then finally, we'll do oxygen. So 6 to the 12, 12 by 15 on the right hand side, left hand side, 15 by 2O2. So this is liquid, this is gas, and this is also gas. So for 1 mole, we can say delta H minus delta U is equal to delta N is equal to how much? Delta N is equal to 6 minus 15 by 2, that is 7.5. It is equal to 6 minus 7.5 is equal to 1.5. So 1.5. So for 1 mole, of benzene combustion, delta N value is 1.5. For 2 moles, automatically delta N value becomes 3. So delta N becomes 3. So for 2 moles, because they have asked for 2 moles, for 2 moles of benzene, this is for 1 mole of benzene. For 2 moles of benzene, delta N is equal to how much? Delta N is equal to, automatically it becomes 3. So delta n is equal to 3 means delta H minus 3 into 8.314 into temperature, that is 298 kelvins. 3 into 8.214 into 298. So if you multiply this, you will get the answer. So 3 into 8, 2.8 point, and you will get the value in negative because this is minus 1.5. So minus 3. So minus 3. So minus you will get value. I hope you can do multiplication. So let us check the answer now. So it is equal to minus 7.43 kilojoules. Means the answer you will get it in joules by divided by 1000. Means you have to convert them into kilojoules. So whatever the answer, you will get it in joules. That is, let us say 7430 joules. So it can also be taken as minus 7.43 kilojoules. I hope it is clear. So in this way you have to calculate. Because they are given for 2 moles. If they are given for 1 mole, because this is for 1 mole. For 1 mole it is 1.5. For 2 moles means it should be minus 3. Because 1 mole of benzene only we have taken here. So for 2 moles means you have to take minus 3. So delta n is equal to minus 3. I hope it is clear. So this type of questions are important. Already we discussed the same question in different pattern in the previous class. Now this is the answer. I hope it is clear. Next question. Now standard state and standard enthalpy reactions. Standard state and standard enthalpy of the reaction delta R HF. I told you, as I told you, delta HF degree or delta RH. That is a reaction. For formation, we'll say delta H F. For reaction, we'll say delta HR degree. Degree should be there. Let us see now. The standard state, also called the reference state of a substance, is the most stable state of the pure substance, that is gas, liquid or solid. At what is the standard conditions? 1 bar pressure or 1 atmospheric pressure, and at 298 kelvins, or it is any specified temperature. So if a substance is present in solution, it should be at 1 molarity concentration. I hope this is called standard state and standard enthalpy. So standard state means 1 bar pressure, we'll say 1 bar pressure, or 1 atmosphere. Both are same because 1 atmosphere is equal to 0.987 bars. 1 atmosphere is just slightly, bars are slightly higher than atmospheres. So 0.987 bars. So straight away we'll take both equation as 1 and 1. And temperature is 298 kelvins, that is 25 degrees C. So this is called standard comparison, standard state. So at this state, it is the most stable state of pure substance, that is gas, liquid or solid. I hope it is clear. Next, continuation. The standard states of few elements are carbon, graphite. So what is the standard state of carbon? Carbon is existing as graphite. Sulfur in the form of rhombic sulfur. Bromine in the form of liquid. That's why bromine is the only liquid non-metal at room temperature. So liquid bromine. So the standard enthalpy of a reaction is the enthalpy change for a reaction when all the participating substances, that is the reactants and products, are in their standard states. So what is standard enthalpy change? Standard enthalpy of a reaction delta HR degree is equal to the standard enthalpy change for the reaction when all the participating substances are in their standard states, that is delta H, that is sigma delta H of products standard state minus sigma delta H standard state of reactants. So delta H of products means delta H of reactants, but delta H degree, sigma delta H degree of products means sigma delta H degree of reactants. So this is called, or when they all are in their standard states, we'll say it is called standard heat of formation of reaction. Heat of reaction, standard heat of reaction is equal to sigma standard heat of formation of products minus sigma standard heat of formation of reactants. I hope it is clear. So why this we are taking, because these are very important in numericals. Now enthalpy change that accompanies the melting of 1 mole of a solid substance in its standard state is called standard enthalpy of fusion. So for melting of 1 mole of a solid substance into melting of 1 mole of a solid substance into liquid, whatever the heat is formed, whatever the heat is taken at standard condition, it is called molar enthalpy of fusion, that is delta H, because the process itself is called fusion. So delta standard enthalpy of fusion is equal to 6 kilojoules per mole. This is the observed value. Standard enthalpy of fusion. Standard enthalpy of fusion is equal to standard enthalpy of fusion, or molar enthalpy of fusion of ice is equal to 6 kilojoules per mole. So it means what? We require 6 kilojoules per of mole to convert solid 1 mole of ice into 1 mole of water at 298 kelvins and 1 atmospheric pressure. At 298 kelvins and 1 atmospheric pressure. So simply I write here the statement at 298 kelvins and 1 atmospheric pressure or 1 bar pressure, 1 atmospheric pressure, to convert 1 mole of ice into water, 1 mole of ice into water, into 1 mole of water, we require 6 kilojoules of heat. 6 kilojoules of heat. So this is called molar enthalpy of fusion. So to convert 1 mole of ice into 1 mole of water at 298 kelvins and 1 atmospheric pressure, we require 6 kilojoules of heat. So this is called standard heat of fusion. Standard heat of fusion. Standard means degree also will be kept here. So this is delta H of fusion is equal to 6 kilojoules per mole. I hope it is clear. So this statement please note down your classroom. At 298 kelvins and 1 atmospheric pressure, to convert 1 mole of ice into 1 mole of water, we require 6 kilojoules of heat. I hope it is clear. Next. Amount of enthalpy change during phase transformation. So amount of heat required to vaporize 1 mole of a liquid at constant temperature. Amount of heat required to vaporize 1 mole of a liquid. So to convert liquid into vapor. So the amount of heat required to vaporize 1 mole of a liquid at constant temperature and a standard pressure, 1 bar, is called standard enthalpy of vaporization or molar enthalpy of vaporization. So delta H of vaporization. So same process, we convert one liquid into gas. So it is called enthalpy of vaporization. It is equal to 40.79 kilojoules per mole. So what is the statement you write here? So we write the statement as to convert 1 mole of liquid water into water vapor at 298 kelvins and 1 atmospheric pressure or 1 bar pressure, we require 40.79 kilojoules of heat, kilojoules per mole of heat energy. So this is called standard heat of vaporization. Standard heat of vaporization, because the process name is called liquid is converted into vapor, so it is called vaporization. So standard heat of vaporization is 40.79 kilojoules per mole. I hope it is clear. So solid to liquid, melting, and liquid to gas, it is vaporization. Next, the standard enthalpy change, the standard enthalpy of sublimation, that is from liquid solid directly to gas, solid change directly to gas, is the change in enthalpy when 1 mole of a solid substance sublimes at a constant temperature, that is 298 kelvins, under standard pressure, that is 1 bar. So it is equal to delta H of H degree of sublimation, that is standard enthalpy of sublimation is equal to 25.2 kilojoules per mole. Stronger the intermolecular force of attraction, higher is the enthalpy of phase change. So if the intermolecular force of attraction is more, so automatically enthalpy of phase change is also very stronger. So I hope it is clear. Next. Now, heat produced by burning 1 mole of a liquid ethanol. Just see here now. Heat produced by burning 1 mole of liquid ethanol C2H5OH into oxygen gas to produce carbon dioxide gas and liquid water at 1 bar is 1 bar. It is equal to 1367 kilojoules per mole. Write the thermochemical equation. Thermochemical equation is simple. It is so ethyl alcohol, ethanol plus oxygen gas gives rise to carbon dioxide plus water. Any organic compound when burns in oxygen, it forms carbon dioxide and water. Now balancing 2 moles of carbon. First we balance carbon, Next, total 6 hydrogen, so 3 moles of hydrogen. Next, finally, we have to do oxygen. So here 1 oxygen, and here 2, 3, and here it is 2 plus 2, 2 to the 4, and 4 plus is 7. So it is already 3 is there, 7 is there. So simply we can say 3O2. So 3O2 because 6 plus 1, 7, and here 2 to the 4, 4 plus is 7. So this is a balanced chemical equation. And what they're asking, write the thermochemical equation. So heat produced by burning 1 mole of liquid ethanol in oxygen gas to produce carbon dioxide gas and liquid water at 1 bar is 1 T. So heat of formation, that is heat produced by 1 mole of liquid. So heat produced means delta HF is equal to heat produced as it is producing heat. So heat of formation is equal to, so you can say heat of reaction, standard enthalpy of the reaction. So here we have tried, again it has gone everything. So please note down this equation. So first answer A is equal to C2H5OH plus 3 moles of oxygen giving rise to 2 moles of carbon dioxide plus 3 moles of water, and plus delta HF is how much? 1367 kilojoules per mole. 1367 kilojoules per mole. This is the equation, thermal equation. Or you can say delta H is equal to minus 1367 kilojoules per mole. Delta H degree F. Next, similarly, what is the mass of ethanol to be burned to get 4 and 10 to the power of 3 kilojoules per mole? So for burning 1 mole, we got for 1 mole, we got 1367 kilojoules per mole. And this is mass of ethanol to be burned. So here, for 1 mole of ethanol, we have to take into consideration again mole concept. So mass of ethanol is how much? Energy of ethanol is given as 4 into the power of 3 kilojoules per mole. So ethanol, what is the molecular weight? C2 means carbon 2, 24, plus hydrogen 5, 5, plus oxygen 16, plus 1. So 24 plus 1, 25, 25 plus 5, 30, plus 16, 46. So what is the molecular weight of ethanol? 46. So for burning 46 grams, when 46 grams of ethanol is burned, it gives this much of energy. Similarly, when how many grams of ethanol is burned to give this much of energy? It means, implies, so X is equal to 46 into 4 into 10 to the power of 3, because 1 mole divided by 1367. If you calculate this, you'll definitely get the answer. So please note it down. Very, very important numerical. So mass of ethanol is equal to 134.6 grams. How many grams? It is equal to 134.6 grams. This calculation part, you can do it easily. So it is equal to 136.4 grams. Sorry, 134.6 grams. 134.6 grams. You should get the answer. So please check it. 100% you'll get the answer. I hope it is clear. So this is called formation of ethanol. So this is the first answer. The second answer is this. How to calculate second answer? So for this delta H is given. So for burning 46 grams, require this much of energy is given out. So to burn how many grams, this much of energy is formed. That is 4 into the power of 3 joule. How we got 46? The molecular weight of ethanol is 46 because 1 mole of ethanol means, because they have given not the mass, they are asking mass. So that's why you get the answer like this. I hope it is clear. So please note it down in your book. Next question. So next topic in this chapter, continuation. So please, next topic in this chapter now we are going to do. Let us see. Factors on which heat of reaction depending. Very, very important. The enthalpy of a reaction depends on the following factors: physical state of reactants and products, and quantities of reactants. So physical state of reactants and products, and also the quantities of reactants. Let us see now. So allotropic modifications. First factor is physical state of reactants and products. Second factor is quantities of reactants. Third one, allotropic modifications. For different allotropic forms of the substances, different amount of heat is evolved or observed. For example, carbon in the form of graphite forms carbon dioxide. In this case, the delta H is 393.5 kilojoules per mole, whereas in case of diamond, it is slightly more, that is minus 395.4 kilojoules per mole. So that's what the allotropic modifications, for different allotropic modifications, forms of the substances with different amount of heat is observed. Next factor is temperature, and fifth one is whether the reaction is carried out at constant pressure, constant volume. So all the 5 factors are important. So let us see. So factors based on this, these 3 are very important. So that is allotropic modifications, temperature, and whether the reaction is carried out at constant pressure, constant volume. Next, types of enthalpies. Very, very important. First one, enthalpy of formation. Enthalpy of combustion. For combustion reactions, we'll say enthalpy of combustion. For neutralization reaction, enthalpy of neutralization. So if whenever a salt means when an acid combines with base to form salt and water, in that case, the heat of reaction is called enthalpy of neutralization. Enthalpy of neutralization. I hope it is clear. So it is called enthalpy of neutralization. Next we have enthalpy of hydration. So when you add water molecules to a given molecule, it is called enthalpy of hydration, enthalpy of transition. So these are the different types of enthalpies we have. Not only this, so many other things. Enthalpy of sublimation is there, enthalpy of dissolution is there. So many things we have. Let us discuss all this. So what is enthalpy of formation? The enthalpy change produced when 1 mole of a substance, very important here, it is 1 mole. When 1 mole of a substance is formed directly from its constant elements is called as enthalpy of formation. For example, formation of ethyl alcohol. So carbon, 2 moles of carbon plus 3 moles of hydrogen plus half mole of oxygen to form ethyl alcohol. So heat of formation means only for 1 mole you take. We will not take for 2 moles, we will take for 1 mole. So it should be equal to minus 277 kilojoules per mole. Similarly, heat of formation of water you can see here. So hydrogen gas combines with oxygen gas to form 2 moles. 2 moles, 2 moles, it is equal to 571.6. But heat of formation for this reaction is minus 571.6 divided by 2. Why? Because we have taken 2 moles of hydrogen. So minus 285.1, because 1 mole of a substance only is formed. So it is called as heat of enthalpy of formation or heat of formation of a compound, may be negative or positive. I hope it is clear. So heat of formation of compound can be negative or positive. Let us continue now. Enthalpy of formation, standard enthalpy of formation. It is an enthalpy change produced when 1 mole of a compound, same process, but in its standard state, that is at 1 bar and 298 kelvins, from its elements also in the standard states. So that is 1 bar and 298 kelvins. So all should be, the reactants and the product should be in standard states. Standard state means it is taken at 1 bar pressure and 298 kelvins. So that is called heat of formation, standard heat of formation, standard heat of formation. So this already we discussed. So standard enthalpy of formation or standard heat of formation of every element in its standard state is assumed to be 0. So the standard heat of formation at its standard state, individual element is assumed to be 0. For example, graphite 0, diamond is also 0, but diamond cannot be equal to 0. The standard enthalpy of formation of H plus or H3O plus in aqueous solution is also taken as 0. So very, very important point this is. Individual elements, it is assumed to be 0. For molecules, it is existing, but for individual elements, it is assumed to be 0. Next, let us take into consideration this question now. 39.35 kilojoules of heat is liberated during the formation of 4.4 grams of carbon dioxide from carbon and oxygen. Calculate the heat of formation of carbon dioxide. So heat of formation of carbon dioxide delta HF is equal to how much they are asking. So first you write the equation C plus O2 gives rise to CO2. So for producing 1 mole of carbon dioxide, 1 mole of carbon dioxide, what is the heat of reaction? So they have given for 4.4 grams of carbon dioxide, how much heat is liberated? That is 39.35 kilojoules per mole is liberated. So they're asking for heat of formation of carbon dioxide. So for 1 mole it is how much? So 44 grams it is how much? So that is equal to 44 into 39.35 divided by 4.4. So 4.4 goes 10 times. So it is nothing but 393.5 kilojoules is the answer. 393, I'm writing it again. 393.5 kilojoules is the answer. Let us check the answer now. So it is minus 390 because heat of formation, because liberated means you have to keep minus sign. So I forgot to keep minus sign. So simply it is minus sign. This is also minus sign. So minus 393.5, minus 393.5. I hope it is clear. So this is called heat of formation. So because they have given when 4.4 grams of carbon dioxide is burned, is formed from carbon and oxygen, this much of heat is liberated. So for this 4.4 grams, it is equal to how much? 0.1 mole. So for 4.4 grams, it is 39.35. So 1 mole of carbon dioxide, we already know the molecular weight of carbon dioxide, carbon 12 plus oxygen 32, it is equal to 44. So for 44 grams, it is how much? Because they're asking heat of formation of carbon dioxide. So it should be 1 mole. So 44 grams. So 44 means 44 into 39.35 by 4.4, which is equal to 393.5 kilojoules per mole. Heat is liberated, so you have to keep minus sign. I hope it is clear. So this type of questions easy and very important also. Next question. Next topic. So enthalpy of reactants and from the enthalpy of formation. Enthalpy of reaction from the enthalpy of formation. Let us see now. Enthalpy of reaction from the enthalpy of formation. So already we know standard enthalpy of the reaction is equal to sigma, that is sum of standard enthalpy of products minus Bi, that is standard enthalpy of reactants. So Ai, Ba are the stoichiometric coefficients. So we have to take into consideration stoichiometric coefficients of reactants and products in the balanced chemical equation. So what is the meaning of this? For example, if I say here 2H2 plus O2 gives us to 2H2. So for this reaction, delta H degree of F heat of reaction is equal to 2 delta H of products, that is delta standard state, delta H degree of products. What is the product? We have hydrogen. For hydrogen, how much? 2H1. So 2 into 2 plus delta H of water into 2 delta H of hydrogen. Sorry. For parts, we have to take parts first. So 2 into delta H of formation of water minus 2 into delta H of formation of hydrogen gas minus, that is plus, reactants delta H of formation of oxygen gas. So in this way, you have to take delta H. I write it clearly if it is not clean. So that is delta H of formation of oxygen, because oxygen it is only 1 mole. So that's why you are taking 1. For hydrogen, it is 2 moles, so we are taking 2. And for water, it is 2 moles, so 2 into delta H of formation of water. So that is what it is called. AI. AI is called 2 here, BI is called 2 here. So that is called stoichiometric coefficients of reactants and products in the balanced chemical equation. So this is called enthalpy of the reaction, standard enthalpy of the reaction. I hope it is clear. Next. Very, very important, Hess law of constant heat summation. Hess's law of constant heat summation. What is Hess law of constant heat summation? If a reaction takes place in several steps, then the standard enthalpy of the reaction is the algebraic sum of the standard enthalpies of reactions into which the overall reaction may be divided at the same temperature. So the enthalpy of the reaction is same irrespective of whether it is carried out in one step or in several steps. For example, let us see, consider A changes to D. So this is the equation. For this is delta H of the reaction. Now, in this case, as A is changed to D directly, so we can write the first, it should say A is changed to B, this is delta H1, and B is changing to C, this is delta H2, and C is changing to D, this is delta H3. Let us say, for example. Now, delta H of the reaction A to D is equal to, so delta H of the reaction is equal to, for this case, equal to delta H1 plus delta H2, sum of algebraic sum, plus delta H3. So this is nothing but what? The algebraic sum of the standard enthalpies of the reaction, standard enthalpies of the reaction. So this is called Hess law of constant heat summation. This is called what? Hess law of constant heat summation. If the reaction is taking place in one step or in several steps. So the overall reaction is equal to the sum of the algebraic sum of standard enthalpies of reaction. So the enthalpy of the overall reaction is equal to the sum, algebraic sum of the standard enthalpies of the reactions. For example, let us take conversion of A to D. So the standard enthalpy of the reaction is equal to delta H degree R. Delta H degree R is equal to delta H1 degree plus delta H2 degree plus delta H3 degree. That is standard heat of formation of first reaction, that is A to B. Then formation of heat of reaction at second reaction, that is B to C. Then third, C to D. Because A changes to D means directly it should not take. So it should take all the steps into conversation. It is taking one step or in several steps. I hope it is clear. Next. Consider a process involving the conversion of reactant A into B in one step, path 1, or in two steps, path 2. Then according to Hess law, so A to B directly changes to path 1, that is H1, delta H. For A to B, first it changes from A to C, then C to B. Then it is step 1 and step 2, as I told you. So delta H of this reaction is equal to delta H1 plus delta H2. Simple it is. So this is called Hess law of constant heat summation. Hess law of constant heat summation. Next, one-step reaction. So for example, consider this reaction: carbon plus oxygen gives us carbon dioxide. Delta H is minus 393.5 kilojoules. The same step can be formed in two steps. Why? Because first it should form carbon monoxide, then it should form carbon dioxide. So first you take C plus half O2 gives us to CO. This delta H1 is equal to minus 110.5 kilojoules per mole. Then CO plus half O2. Then second step what happens? CO plus half O2 gives us CO2. Then delta H2. So delta H is equal to delta H1 plus delta H, that is minus 110.5 minus 283. That is, you should add these two, then keep minus sign. So automatically you get minus 393.5 kilojoules. So this is called application of Hess law of constant heat summation. Application of Hess's law of constant heat summation. I hope it is clear. It's very, very easy to understand. So on the whole, what is that reaction? So delta H of the reaction is equal to delta standard heat of formation of the reaction is equal to. So if the reaction taking place, for example, in three steps, then standard heat of formation of first step, that is delta H1, plus standard heat of formation of second step, that is delta H2, plus delta H3, and so on. I hope it is clear. So please note it down. So this is called Hess law of constant heat summation. Hess's law of constant heat summation. If the reaction is taking place in one step or several steps, then the standard heat of formation of the reaction is equal to the sum of the algebraic sum of the reactions, sum of the heat of reactions of the algebraic sum of the heat of reactions taking place in several steps. So delta H is equal to delta H1 plus delta H2. I hope it is clear. Next. Lavoisier and Laplace law. This is not there in your examination point of view, but still it is important. That's why I have given discussion. The amount of heat liberated or absorbed during a chemical reaction is equal to the amount of heat absorbed or liberated when the same reaction is carried out in opposite direction. So, for example, you see H2 plus half O2 gives H2, H2 delta H in this case minus 286 kilojoules per mole. Similarly, if you take reverse of this reaction, that is H2O is giving rise to H2 plus half O2. In this case, how much heat is required? This is called plus 286. So this is called as Lavoisier and Laplace law. According to Lavoisier and Laplace law, the amount of heat liberated or absorbed during a chemical chain reaction is equal to the amount of heat absorbed when the same reaction is carried out in opposite direction. That is backward reaction. So backward reaction and forward reaction, what are the amount of heat is required? It is same, but with opposite sign. So that's why in the formation of water from hydrogen and oxygen, we got delta heat of reaction is equal to minus 286 kilojoules. Whereas the formation of hydrogen and oxygen from water, that is reverse of the first equation, we got it is equal to plus 286 kilojoules. I hope it is clear. Next. Standard enthalpy of combustion, very, very important. Simple it is. Just that formation of the reaction is combustion reaction. So, for example, it is the enthalpy change produced when 1 mole of the substance is completely burned in excess of oxygen, with the reactants and products being in their standard states. It is called as standard enthalpy of combustion. The process name only we write here. So it is denoted by the letter delta H degree C, where standard enthalpy of combustion. So it is called, so heat of combustion or standard heat of combustion. It is always negative because all combustion reactions are exothermic reactions. All combustion reactions are exothermic reactions. That's why always you'll get it as negative. Very, very important. So consider combustion of methane. When 1 mole of methane gas is burned with excess of oxygen, it forms carbon dioxide and water vapor. Since already I told you many times, any organic compound when burnt in air oxygen, it forms carbon dioxide and water only as a product. It forms carbon dioxide and water. So in this case, delta H is minus 890.3 kilojoules. So this is called standard heat of formation, standard enthalpy of combustion of methane. This is called what? Standard enthalpy combustion of methane. I hope it is clear. So please note it down. Next, fuel value or calorific value. The amount of heat produced when from the complete combustion of 1 gram of fuel or food is called fuel value. So when you burn 1 gram of fuel or food, whatever the amount of heat produced, it is called as calorific value or fuel value. Its unit can be in calories per grams or joules per grams. So we know the calorific value of fuel. Higher the calorific value of the fuel, higher is the rate of combustion. So easily it will give out. Easily it is burnt. Let us see now example. The enthalpy of combustion of glucose is, so for 1 mole of glucose they have given enthalpy of combustion of glucose, that is delta H of C is equal to minus 2850 kilojoules per mole. It is for 1 mole. The calculated amount of heat liberated by burning 9 grams of glucose. So for 9 grams of glucose, how much heat is liberated? So we already know for glucose, what is the molecular weight? Molecular weight of glucose is C6H12O6, that is equal to carbon 12 into 6 plus hydrogen 12 into 1 plus oxygen 16 into 6. So it is 96. So it is equal to 72 plus 12 plus 96, which is equal to 180. So we know the molecular weight of glucose is 180 grams. So for burning 180 grams, we this much of energy is liberated, that is minus 2850 kilojoules per mole. Similarly, for burning 9 grams, how much heat is required? They're asking that only. It implies 9 into 2850 by 18, 180, sorry, with minus sign. So 9 ones are 9 20s are, and 0 gets cancelled. 2 ones are 2 142.5 times. So answer is 142.5, that is with minus sign, kilojoules per mole. So it is equal to how much? Minus 142.5 kilojoules per mole. So to burn 180 grams, this much of heat is required. So to burn 9 grams, how much heat is required? So how much heat is liberated? So the enthalpy of combustion of glucose, for burning 1 mole of glucose, we got minus 2850 kilos. This much of heat is liberated. So for burning 9 grams, for when 9 grams of glucose is burned, how much heat is liberated? They are asking. So by using this, we can say 180 grams of glucose giving minus 2850 kilojoules per mole of heat energy. So when 9 grams of glucose is burned, how much heat energy is given out? So that is equal to minus 142.5 kilojoules per mole. I hope it is clear. Let us check the answer. So it is 142.5 kilojoules per mole with minus sign only. Anyway, it is given out, so it already will keep it as, because any combustion reaction is negative. So answer is negative, minus 142.5. Anyway, given out means we have to keep minus sign. I hope it is clear. So like these questions is very, very simple and easy to understand. Let us see now next. Example 3. Calculate the enthalpy of combustion of glucose from the following data. So we need to calculate the enthalpy of combustion of glucose. So first they are given carbon plus oxygen gives us carbon dioxide. It is enthalpy of combustion of carbon. Enthalpy of combustion of hydrogen also they have given minus 269.4. Enthalpy of combustion of carbon for 1 mole it is minus 395. For 1 mole of hydrogen it is minus 269. And to produce glucose, total enthalpy of heat is minus 1169.8. So 6 moles of carbon, 6 moles of hydrogen plus 3 moles of oxygen, it forms C6H12O6. So simple it is. So delta H for the entire reaction is also given. So we need to calculate enthalpy combustion of glucose from the following data. So to find enthalpy of combustion of glucose, enthalpy of combustion of glucose of C6H12O6, enthalpy of combustion of glucose, that is C6H12O6, is equal to enthalpy of formation of, that is products, minus enthalpy of formation of reactants. For products it is 1 mole of glucose, so it is nothing but minus 1169.8 plus minus enthalpy of formation of reactants. Reactants we have 6 moles of hydrogen, 6 moles of carbon. We have 1 mole of carbon, 1 mole of hydrogen. So it is equal to 6 into minus 395 plus 6 into minus 264 minus 269.4. Why we are multiplying with 6? Because for 1 mole it is 269 for 1 mole of hydrogen. But we have 6 moles of hydrogen, so 6 into 269. Similarly, for 1 mole of carbon, it is minus 395, but we have 6 moles, so we have to take 6 into 395. So that is equal to delta H of glucose equal minus 1169.8 minus of this. You have to multiply this, you will get the answer. So what is the answer? Let us check now. Is equal to minus 2816.6 kilojoules per mole. So it should be equal to this. I am rubbing it now. Just you are doing this. So if you calculate this, you will get it as minus 2816 because anyway it's combustion. So if you get even plus also, you should keep it as minus sign. So minus 2816.6 kilojoules per mole. So in this way you'll get the answer. So I hope it is clear. So very, very important. So delta H of products, that is stoichiometric coefficient. Stoichiometric coefficient means 6 and 6 here we have to take. Very, very important. So please note it down. Next. Example 4. Calculate the enthalpy of formation of potassium chloride from the following data. So they have given heat of formation of potassium chloride, that is 57.3. Now they are asking us to form potassium chloride from the following data. First step, it is hydrogen plus oxygen gives us delta H, and delta H in this case water. So here the reactants we have water and HCl is also there. So for that we have to take into consideration this minus 286.2, and hydrogen plus chlorine gives us HCl, that is minus 164.4. So heat of formation of HCl is minus 164.4, and heat of formation of water, because we have water and HCl in the reaction. So and heat of formation of potassium hydroxide is minus 487.4. This is the total equation. So what is the, and here heat of formation of potassium chloride is delta H is plus 18.4. So from potassium hydroxide, we got potassium chloride, and finally they are asking potassium chloride. So straight away, instead of using all these things, straight away you can take potassium plus oxygen plus hydrogen plus gives us to aqueous KOH. So from KOH only they are giving. So KOH is equal to minus 47.4 plus 18.4. So simply delta H of this reaction is equal to delta H is equal to formation of potassium chloride is equal to minus 487.4, because for forming potassium chloride we require potassium hydroxide. From potassium hydroxide only potassium chloride is formed. So minus 487.4 kilojoules per mole plus potassium chloride aqueous, potassium solid aqueous gives rise to potassium chloride. So it becomes plus 18.4. So if you do this, you'll get minus 487.4 minus 18.4. It should be approximately 487 minus 18. So let us check 487 minus 18. It's equal to 467. But here we should take formation into consideration. So let us see here again and do it for your understanding. So take this as first potassium. The starting material is potassium hydroxide. Potassium hydroxide plus HCl gives rise to potassium chloride plus water. So this take it as delta H1, delta H2, because water is formed from this. So delta H2. So delta hydrogen and chlorine hydrogen is found from delta. This is delta H. This is delta H1 plus delta H2. And just do it again. So please note it down. Now you see the delta H for the formation of potassium chloride is 57.3. So for this is delta H1 plus delta H2, because this step is found by using these two, 286.2 plus 164.4, you'll get it as 57.3. So delta H is equal to delta H1 plus delta H2. Next step is delta H of total conversion, that is potassium solid plus oxygen plus hydrogen gives rise to aqueous KOH. How you got this aqueous KOH? By using this reaction, that is minus 47.4. So finally they are asking, this is KCl plus aqueous K gives us to, so this is called delta H3 and this is delta H4. So delta H of the reaction is equal to delta H1 plus delta H2 plus delta H3 plus delta H4 by using Hess law. Then you'll get the right answer. I hope it is clear. Let us check the answer now. You should get it as 441.3 kilojoules. So 441.3, how you got it? So by adding all one delta H1, delta H2 and delta H3 minus delta H4. So you'll get the answer clearly. So delta H minus, sorry. So delta H minus, I'll write it here. Delta HF of benzene. Say let us take it as delta H5. So delta H5 minus, I'll write it again. So 57.3 kilojoules minus all. So if you do by applying Hess law, definitely you'll get the answer. So please again try to do it by applying Hess law, you'll get the answer easily. So how we did in the case of benzene. So by applying Hess law, by applying Hess's law of constant summation, you'll get the answer. So please note it down. So that the same reaction is taking place in how many steps? 5 steps. So delta H of the entire reaction is equal to, simply add all these things, you'll get the answer. Delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H5. So by applying Hess's law of constant summation, you'll get the answer minus 441.3 kilojoules. So please note it down. I hope it is clear. Next. So with this, we are completing this class. So in next class, we'll do more questions based on heat of reactions. I hope it is clear. Thank you all. So please concentrate whatever the examples we have discussed. So in next class, we'll discuss more topics in thermochemistry.